And then we'll go ahead. Hello, everyone. Welcome to yet another session of AFMS seminar series. Today, we have Daniel Lester from RMIT University. It's my pleasure to give a brief introduction of him to you all. Daniel earned his PhD at the University of Melbourne in 2003. He was then a postdoc in the Advanced Thermofluids Lab at CSIRO, and later a research scientist at the Mathematics, Statistics, and Informatics division of the same organization. And this was before joining the School of Engineering at RMIT University in 2014. Daniel uses computational and theoretical methods to pursue fundamental and applied research problems on various topics, one of which he's going to talk about today. So over to you, Daniel.
Thank you, Vishal. I've just got a couple of icons on my screen I can't get rid of. Just bear with me a sec. I might just stop sharing and reshare if that's okay.
Yeah, that's all right.
I'll just share the application, I think might. Is that coming through for you people?
Yes.
Okay. Do I need to, is that full screen or?
No, not yet. No.
Not yet. Okay.
Yeah, it is now.
Okay. All right. With that. Okay. So thank you, everyone. And welcome to a talk. Today, I'm going to talk about fluid mixing in porous media, which is a topic we've been sort of looking at one way or another for the last decade or so. We're going to look at mixing in fluids of arbitrary complexity. And the image over here on the right is an example of some of the complexity that can arise in what is generally described as a very simple porous media flow. There is a drop of fluorescing particles, PIV particles, that are then dropped through a slow Stokes flow over a column of packed glass beads. And as you can see, in a short space of time, that plume of tracer particles forms a very complex distribution of sheets and fingers and such forth that is characteristic of chaotic mixing. And so this points to an example of when we really drill into the details, a lot of these previously considered simple flows are actually quite complex. And the question is, how do we then characterize and understand and control mixing in these processes? And we're going to scale from very simple flows at the pore scale through to regional scale flows and everything in between. I'd like to acknowledge collaborators who have worked in this space over the years. Marco Dents at CSIC in Spain, Tanguy Leborn at the University of Rennes in France, Sylvie Lethoire and Alexander Vrallet in France and Norway, Joris Heyman at the University of Rennes, Guy Metcalf and Mike Trefai, who were sort of the originators of getting into this work, worked for over 10 years in this space at CSIRO and other institutes, and Aditya Bandapahey at IITB in India. So the outline today, I'm going to talk a bit about the motivation of considering fluid mixing in flows of arbitrary complexity. We're going to look at some complex flow examples, some of the challenges and considerations of how to characterize mixing, classification of various porous media flows from simple to complex. And then we're going to present a general framework for how to characterize solute mixing across this very broad range of flows. We're going to look at examples then of application of that framework to steady flows and unsteady flows, and then I'll summarize at the end. Okay, so the motivation, I'm going to take a little bit of a sidetrack here in terms of motivation, just to look at an example of a complex flow in porous media that has a lot of impacts in neuroscience, and that is poroelastic flows in the brain. So this is work with some of the collaborators in France and Norway. We're looking at the poroelastic flow of cerebral spinal fluid. And essentially what happens is in the arteries, around the arteries and veins within the brain, there are these perivascular spaces, and they're subject to different pressure signals due to respiration and cardiac signals, but also low frequency waves that arise during REM sleep and so on. And it's well recognized that that poroelastic flow that's set up by these oscillations drives the clearance of waste in the brain, and poor clearance of that brain is linked with a number of neurodegenerative diseases, including Alzheimer's and Parkinson's. What's been found is that during REM sleep, these pressure oscillations are associated with clearance, but the poroelastic mechanics and the details of transport are not well understood at all. So studies have shown that sleep deprivation impairs molecular clearance, and then more recent work has shown that there is a direct correlation between the oscillations in this perivascular space during the awake and sleep modes that are quite different, and you get very different transport dynamics that come out of that. So the mystery to be unpacked here a bit is, how do those pressure oscillations couple together with the poroelasticity of the brain space and the cerebral fluid within that lead to altered transport characteristics, and that ties back again to these neurodegenerative diseases. It's recently been shown that this perivascular spaces indeed can be represented as a heterogeneous porous medium, and the question is then, can we actually build models and so on of this process to better understand and characterize these illnesses? So I guess that's an overview of some of the ways that complex flows in porous media can lead to important changes in biological systems. The motivation for today is to take this problem as an example of complex transport, but also think about simple systems like we looked at earlier with packed spheres, and think about how can we characterize and understand solid transport in those systems. There's a range of new experimental and computational methods that allow us to resolve transport and mixing at the Porous and Darcy scales with unprecedented resolution. And the question is, how can we use these to predict solute transport? So modern techniques using micro PIV or micro CT scanning. We have very good experimental data sets that show these transport processes at the pore scale. The question is, what can we do with this avalanche of data? And as I've stated, these flows range from simple flows, so we can think about steady flows that are two-dimensional flows. They may be non-chaotic in model systems, through to quite complex flows that may be unsteady. They have a three-dimensional character. They could be chaotic. And there's a broad range of transport phenomena that can fall under this range. The complexity of these flows is characterized by what we call the Lagrangian kinematics, or in some sense, the flow topology. And when we consider simple flows, they are associated with constraints on these Lagrangian kinematics and then solute transport. So where fluid particles go is obviously going to dictate where transport occurs, and even in the presence of diffusion. That's quite important. What we're really after is a framework that allows us to classify, analyze, and quantify solute transport across these diverse flows that, on one hand, honors the kinematic constraints, but also opens the door to be able to capture this complexity. And at the end of the day, these are, for heterogeneous porous materials, these are essentially stochastic problems, because we don't know the exact heterogeneity. We don't know the exact structure of these materials. We might have some statistical classification, but we need to be able to capture, on one hand, the stochastic nature of these flows, and on the other hand, the coherent nature of them. So let's look at some examples. If we consider steady pore scale flow, we found, and as we stated on the first slide, that these are inherently complex. Previous work that our group has performed has found that the pore scale topology, so whether we talk about porous networks or granular media, this will generate chaotic mixing under steady flow. And this is due to the presence of saddle points or contact points that generate exponential stretching of fluid elements. So for granular materials, the contact points between grains act as a saddle type point, and associated with that saddle type point is strong exponential stretching of the fluid locally. And for pore networks, we find that the presence of saddle points is tied up with the Euler characteristic of the porous material, which is generally very large, generally very strongly negative. Or we can think about the topological genus being strongly positive. That essentially, from the Poincaré-Hopf theorem, tells us that we're going to have a large number of saddle points in our flow. And a large number of saddle points is then associated with local exponential stretching. So the topological complexity that's inherent to porous media at the pore scale also leads to exponential stretching, no matter what type of porous media you have. And this fluid stretching, as fluids flow through the porous architecture, these fluid elements are stretched and folded during the advection process, and there's a strong link between this process and the grain structure for granular materials. So we can look here, we have a plume of a dye in these experimental images flowing from right to left. We have a number of spheres that have been indicated here, but in fact, this plume is sitting within a index matched glass bead pack with a fluid saturated throughout. And we've just highlighted a number of beads to show them. And you can see very quickly that this plume breaks up into quite a complex structure. And this complex structure is actually understood as stretching and folding of fluid elements that arises at the contact points between grains. Other studies have found very similar dynamics, and this is now well understood to be the mechanism for solute mixing at the pore scale. In unsteady flows, we can also look at what's known as a push-pull flow, where essentially we perform a similar sort of experiment. We have a glass column here, and in this glass column is packed glass beads. These glass beads are invisible because the fluid that's sitting in that column has been index matched. And so we can pump a solute fluorescent dye into this glass bead pack and then withdraw it. This is our push-pull flow. And by characterizing the fluid, the solute distributions that come at the plane where we're imaging, we can then understand some of the mixing characteristics of the flow. The net deformation that occurs over that push-pull phase is 0 because the flow is fully reversible. But there will be signatures of highly heterogeneous and anisotropic dispersion, and that is essentially a diffusive signature of those stretching and folding motions. So the video that we'll show here on the right shows the withdrawal of a plume at that imaging plane, and so you can see that that starts off as a ellipsoidal type shape, which is the shape of the plume as it was injected, and then as we withdraw it, it then takes on a highly ramified and heterogeneous structure, and that structure is holds important information regarding the mixing characteristics at the pore scale. Now, this is really useful. Obviously, in this experiment, we have a index matched fluid and it's fully transparent, so we can see exactly what's going on. But if we have less ideal materials that obviously most materials we can't see through are not optically clear, this allows us to characterize the mixing dynamics within the pore structure. So analysis of this solute distribution allows us to characterize this chaotic mixing at the pore scale. We can also look at steady Darcy flows, so zooming up from the pore scale to the Darcy flow. In three-dimensional anisotropic porous media, we find that steady Darcy flow can generate complex flow behavior. And this is associated with non-stationary conductivity fields that drive strongly helical flows. And those helical flows, both experimentally and numerically, give rise to mixing dynamics like those shown in the bottom right here. So zooming up from very small scales to very large scales, we can still see quite complex flow behavior given the sufficient ingredients are present. For unsteady Darcy flows, the ability to pump flows over time generates very complex transport dynamics. On the top right here, we have a series of images of a pumping experiment, and the amount of reaction that takes place is indicated by these colored regions. There's a light sensitive, a chemical reaction here that produces light emitting species. So the amount of reaction that takes place is proportional to the amount of reaction that's taken place. So in the top image, we have a transient flow where we are pumping fluids in and out over time, and you can see that that produces much larger reactant products than the other case, the control underneath where we have steady flows. So this idea of pumping flows over time then produces quite significant changes in chemical reactions and mixing. We can also consider a poroelastic system. Here we have a regional flow, so shown down in the bottom left here is a heterogeneous medium subject to a regional flow from right to left. And on the left-hand boundary, we have an oscillatory pressure boundary. Now, because the material is slightly poroelastic, when that oscillatory boundary is imposed, you can see pressure waves moving through the system. The colors here are vorticity, where blue is negative vorticity and red is positive vorticity. And so these pressure waves that propagate through the medium then impart some transient dynamics to the flow. And when we look at the transport dynamics in terms of tools known as Poincare sections, which essentially are a stroboscopic map the transport of particles at integer multiples of the forcing period, we get these very complex transport structures. We get isolated mixing regions, we get non-mixing islands, we get stochastic layers, all sorts of transport dynamics are occurring here that are not possible under steady flow conditions. And so we believe there is a strong link between the dynamics that we're seeing in this sort of flow and the poroelastic brane clearance problem shown on the first slide. In the bottom right, we see a series of images of the streamlines of this flow averaged over time, and increasing from top left to bottom right is the compressibility of the poroelastic medium. So you can see for a fairly inelastic medium, the average transport is the same as for a steady flow, but as the compressibility of the medium increases, we see bifurcations and new transport dynamics arising, such as these closed islands here that are essentially barriers to transport, and eventually a bifurcation towards chaotic dynamics. So in flows that are otherwise quite simple under steady conditions, the impact of transient dynamics changes that markedly. So the challenges and considerations that we have is, how do we house all of these dynamics into a single coherent framework? Some of the things we need to consider is chaotic mixing. So what is chaotic mixing? Essentially, it's a recognition that the advection equation under certain circumstances is a dynamical system. And if the degrees of freedom are sufficient, i.e. 3, we have 3 degrees of freedom, i.e. the system is 2-dimensional and transient, or 3-dimensional and steady, or 3-dimensional and unsteady, there's enough degrees of freedom in this system to generate chaotic dynamics. So the advection equation itself, which transports particles over time, we can consider that to be a dynamical system, and the question is whether that dynamical system admits chaotic dynamics or not. The underlying flow itself may be quite regular. We might be in the Stokes regime or laminar regime, for example, but the resultant Lagrangian kinematics are chaotic. This typically manifests as stretching and folding of fluid motions, and that leads to exponential stretching of fluid elements. And we can characterize that the strength of that chaos by the Lyapunov exponent lambda infinity. So essentially, material elements will grow as e to the lambda infinity times t. And we can see an example from the earlier experiments here of the stretching and folding of a difilament as it moves through a 3-dimensional bead pack, and you can see the characteristic stretching and folding of that filament. And when you analyze that, you indeed find that that's growing exponentially with time. The folding is a necessary step to hold the exponentially stretched material within a finite, or at least a volume that grows as algebraically with time. So the take-home point is that as long as these degrees of freedom exist, chaos is the norm in random and Porous and Darcy scale flows. The only time that you won't get it is if other constraints, other kinematic constraints may come into play in the system. Another concept that we want to hold in mind is the braiding of streamlines. Very often in steady and unsteady flows, chaotic trajectories can manifest as streamlines or path lines that braid in space or time. If this braiding is non-trivial, the fluids are stretched exponentially, and indeed we can estimate the Lyapunov exponent up to some constant of proportionality from those braiding motions. So we consider when do, with respect to some measure, when do streamlines or path lines cross over each other. If they make a complex braiding motion, we can calculate what's known as the topological entropy associated with that. And from that, we can then make some estimate of the strength of chaos in the system. The take-home point is that braiding of streamlines is observed widely in many Porous and Darcy scale flows without the recognition that these are actually chaotic. So we can look at simulations of Porous scale flow or anisotropic Darcy flows, and indeed we find quite regularly we find this complex braiding of streamlines, and so from that we would surmise that indeed there's a good chance that these flows are indeed chaotic. Another concept that's quite relevant for some of the model flows that are considered in fields of porous media is helicity. And helicity is also used heavily in turbulence studies to measure the complexity of the flow topology. Essentially, the helicity is given as the dot product of velocity and vorticity. And if the helicity density is 0 everywhere for a steady flow, we can surmise that that flow is non-chaotic. So this came from earlier work of Moffat, and then now Arnold has built on that as well. All steady two-dimensional flows are helicity free because the vorticity is always going to be normal to the velocity. But also there are some steady 3D flows that are also helicity free. And some of these are quite relevant for flow in porous media. One of these is isotropic Darcy flow, where the velocity is given by the product of the permeability K and the potential gradient or the pressure gradient, grad phi. And for these types of flows, just from vector identities, you can show straight away that the helicity is everywhere 0 because the vorticity is always perpendicular to the velocity. Now, this has very important implications for the grunging kinematics and mixing, because these 3D helicity-free flows have been shown to admit a pair of stream functions under certain boundary conditions. And so if that is the case, these stream functions then act as invariants of the flow and then constrain the grunging kinematics. Essentially, these stream functions can be considered to be invariants, and because they are invariants and we have two invariants in a steady three-dimensional flow, then this flow is integrable, i.e. it's non-mixing, and it can be described as streamlines in terms of streamlines that do not braid. So essentially, the helicity-free nature of this quite important class of models of flow in porous materials then lead to stream functions that essentially preclude braiding and transverse mixing and macro dispersion. So for these sorts of flows, we have these organizing sets of stream functions, and they essentially strongly constrain the dynamics, whereas you can see in the top right figure here, for anisotropic Darcy flows, we have much richer dynamics, and now we can see braiding and knotting of streamlines, and that has important implications with respect to mixing and transport. We also need to account for the fact that mixing can be singular, in that in the limit of vanishing dispersivity, this is not the same as having a 0 dispersivity case. For example, if we consider the advection diffusion equation and we look at the scalar dissipation rate, if that flow is chaotic, then the limit of vanishing dispersivity still gives, no matter, even if that dispersivity is arbitrarily small, the rate of mixing is still non-zero. Whereas for a non-chaotic flow, we have a singular limit, and the rate of mixing goes to 0 as the diffusivity goes to 0. So this means that the presence of these chaotic mixing dynamics fundamentally alters solute mixing and dispersion, and has impacts in terms of biochemical reactions and so forth. The other factor we need to take into account is that solute mixing and solute transport is tensorial, and by that we mean there are distinct longitudinal and transverse components to dispersion and mixing. So if we were thinking of a line source shown by the vertical green line in the bottom right here, if that was continually injected, that would form a two-dimensional sheet. And if we were interested in mixing, we'd be interested in how that sheet was folding back on itself as shown by the blue line. And in that case, we'd be interested in transverse mixing. If on the other hand, we considered a pulsed line source, then that line source is going to evolve within the same sheet, but is going to evolve as a line as shown by the red line there, and then that line may also mix via longitudinal mixing. So there's different aspects to solute mixing and transport that mean it's essentially a tensorial process. And so we need a framework to capture this complexity that's going to house that. Okay. So to zoom out for a second, let's look at the classification of various porous media flows, and before looking at how can we classify and quantify mixing and transport in these systems. We can think about setting up a table here of various porous media flows ranging from flows with low kinematic complexity with a large number of kinematic constraints, so that is shown at the top of the table. And then as we move down the table, we're essentially releasing those kinematic constraints, and we're considering flows with more kinematic complexity. So the simplest flows at the top are steady two-dimensional flows. They're non-helical, they're non-chaotic, and for example, they might be steady 2D or Darcy 2D or Porous Darcy scale flows. We can also consider next down from that three-dimensional isotropic Darcy flows, and as we said that they're non-helical, so they're also non-chaotic. And then more complex than those is then anisotropic Darcy flows, where the flows are now helical and can be chaotic. And what do we mean by anisotropic is that the conductivity or the permeability of the fluid is now a tensor as opposed to a scalar. More complex still are unsteady 2D flows, so 2D Porous or Darcy scale flows. They are not helical, but they can be chaotic. And then the most complex of all is, of course, unsteady three-dimensional flows at the Porous and Darcy scales, which are both chaotic. So the question is, how can we develop a framework that quantifies the Lagrangian kinematics of these diverse flows and allows us to understand mixing and transport in a stochastic sort of framework? And so to present that, we're going to look at the dynamics, basic physics of solute mixing and dispersion. So solute mixing and dispersion essentially comes from the interplay of stirring and diffusion. Fluid stirring can be quantified as deformation, stretching, shearing, folding of material elements, and diffusion is occurring concurrently with that over time. And so the thing that matters is the deformation history governs mixing. If we can say something about what are the fluid deformation events that have occurred in the past up until the present, and at what time did they occur, we can then quantify mixing and dispersion. So once characterized, deformation history and deformation rates can be used to predict mixing. And this has been done very successfully using lamella type mixing theory. It's been applied to steady 2D flows and more recently to 3D flows. And there are moves afoot now to extend those models to unsteady 2D and 3D flows. Essentially, these flows will quantify the concentration PDF and give us some idea about dispersion and transport, and also the mixing within the solute plume. And the ingredients that go into these models is the rate of deformation and the Peclet number. They're quite general. They can range from very high Peclet number flows where there's not a lot of diffusion and you get very ramified solute distributions through to low Peclet number flows that are essentially diffusive and can be almost modeled by a Gaussian blob. So to quantify deformation, the appropriate tool is of course the deformation gradient tensor, and that includes a transform from Lagrangian to Eulerian to Lagrangian coordinates. It's a first order measure, and so it captures the deformation to first order of fluid material elements in Lagrangian coordinates. So we're looking at things like stretching, rotation, and shear of material elements, but it doesn't capture second order effects such as folding and twisting. The deformation tensor evolves via the Lagrangian velocity gradient. We're going to denote that as epsilon of t. So that's the velocity gradient of a material element as it moves along a streamline or a path line. And the evolution equation is shown there. At time equals 0, the deformation tensor is the identity matrix. So that represents a spherical material element. And then that typically will be deformed into some sort of ellipsoidal material element. Because the deformation tensor is tensorial, it has the ability then to capture both longitudinal and transverse deformation. So its tensorial nature already fulfills one of the requirements that we need for this framework. And we can see here now that the deformation tensor, the history of that deformation tensor directly controls mixing. If we consider a simplified example where we have a two-dimensional or three-dimensional Gaussian solute blob, initially at position x naught of naught and then evolves as x naught of t as it's vectored through the flow. It has covariance matrix sigma of t, And that covariance matrix evolves with time and captures both the deformation and the dispersion of the blob. So we can write sigma of t as delta of t plus 2 times lambda of t, where delta of t is the deformation of the blob due to the deformation of the fluid. And so that is essentially a reversible process. So you can see here that delta is equal to the deformation tensor contracted with the initial covariance matrix. And that's essentially the stretching and shearing and compression and so on of that original blob. And that's completely reversible. On the other hand, the second contribution to the evolution of the covariance is the blob dispersion given as lambda. And that's the integral of the deformation tensor contracted with the dispersivity tensor. And that's an irreversible process. So that's showing the production of entropy and the diffusion of the blob that can't be reversed over time. And so we can see here that the history given by that integral of this term over time captures mixing and dispersion of our Gaussian blob. And so if we can characterize the deformation tensor gradient, sorry, the deformation tensor, then we can characterize the contribution to mixing from that. More generally, if we move away from our simplified Lagrangian Gaussian model, we can also pose the advection diffusion equation in Lagrangian coordinates. And when we write that in Lagrangian coordinates, we lose the advection term due to the transform to Lagrangian coordinates. And the diffusion or the dispersion term is augmented by the deformation tensor itself. So the deformation tensor directly gives us a way to predict solute mixing and dispersion from characterization and understanding of the representative diffusion constant. So we need a model for evolution of the deformation tensor, and we do that by moving into a moving and rotating coordinate frame, which we call a protein coordinate frame. Essentially, we follow tracer particles as they move along streamlines and path lines, and we rotate that coordinate frame in a particular way that I won't get into details of at the moment. But essentially, we rotate that in a way that renders the velocity gradient tensor epsilon upper triangular. Now, this has a lot of advantages in terms of computing the elements of the deformation tensor, because now when we go to solve the differential equation that governs the deformation tensor, we have closed form expressions for all of the terms in the deformation tensor. So it simplifies things a lot. Not only that, the velocity gradient tensor in this frame has we can directly understand the physical meaning of the coefficients, such that the diagonal terms of the deformation tensor quantify fluid stretching, whereas the non-zero off-diagonal terms quantify shearing of fluid elements. We can then directly solve the elements of the deformation tensor as simple integrals, and we can pull out the Lyapunov exponents for this flow as the ensemble averages of those diagonal elements of the deformation tensor. So there's a lot of advantages in using this framework. For steady flows, it turns out that this protein coordinate frame are simply streamline coordinates. So whether it's 2D or 3D, if the system has streamlines, then this will be a streamline coordinate frame. For helicity free flows, the protein coordinates also align with the stream functions that we mentioned earlier. And for unsteady flows, there's no such thing as streamlines. We only have path lines, and essentially the protein coordinate frame just tumbles. For steady flows, however, the longitudinal and transverse fluid deformation components are then given by specific components of the deformation tensor. So we can go back to our classification of various porous media flows and then look at what the form of the deformation tensor and the velocity gradient are zero and non-zero in this frame. So we're back at our table that we looked at before of simple flows, kinematically simple flows at the top and kinematically complex flows at the bottom. And we see, first of all, that the number of non-zero off-diagonal terms is increasing typically as we move down. So the number of non-zero off-diagonal terms in the velocity gradient tensor increase in general as with increasing kinematic complexity. But also more importantly is the number of independent non-zero Lyapunov exponents in the system increases as we move from steady, simple 2D flows to unsteady 3D flows. And so this corresponds directly with flows being chaotic or not, in that the non-chaotic flows have Lyapunov exponents of 0 because they're non-chaotic. It's not until we get to steady 3D flows that we have one non-zero Lyapunov exponent in the system. Unsteady 2D flows also have one independent Lyapunov exponent. And then finally, when we get to unsteady 3D flows, do they have two independent Lyapunov exponents? So this velocity gradient in this frame captures the constraints and complexity of Lagrangian kinematics across these broad range of flow classes. How would we apply this to my computational experimental data sets? Essentially, we can just follow a recipe. Given our velocity field, whether it's 2D or 3D, steady or unsteady, we just perform particle tracking to generate our particle positions x0 of t, and then we rotate via a rotation tensor q of t into the protean frame. We determine the protean velocity gradient, so we're assuming that we can also access the velocity gradient of our flow along the path lines, and then we simply gather statistics on the elements of the velocity gradient tensor and the velocity, and we look at the PDFs of velocity and the correlations between them. We can apply this to quite complex flows. So we've done this, for example, to the Johns Hopkins turbulence database, and we get the distribution of velocities along streamlines, of path lines, obviously, and we get the 6 elements of the distributions of the 6 elements of the velocity gradient tensor, and we can look at the correlations between those. In principle, that's enough to start building stochastic models for the evolution of that of the deformation tensor. So essentially, statistical characterization of this velocity gradient tensor in this frame allows us to predict the deformation tensor and thus quantify solute mixing. So let's look at application to this frame. For steady flows, if we assume that we've characterized the velocity gradient tensor, we can then develop a ab initio from first principles continuous time random walk for the deformation gradient tensor. This deformation CTRW captures the stochastic nature of heterogeneous media, but also preserves the underlying Lagrangian kinematics. For steady flows, and especially steady flows in porous media, because remember the porous medium dictates the structure of the flow, the velocity itself and the elements of the velocity gradient tensor decorrelate with distance along a streamline, not time. And this makes perfect sense for porous media because as we move through the porous medium along a streamline, the tracer particles will then sample new parts of the heterogeneity structure, and the correlation structure of that heterogeneous medium will dictate how velocities decorrelate with streamline distance. So previous attempts to build these sorts of models have used time. When you use time as a basis for your random walk models, you have problems with intermittency and so on, which is shown by the velocity distribution on the left graph here. However, when you build a random walk with respect to streamline distance S, we find that in fact the system is truly Markovian and so fulfills the requirements for a continuous time random walk. So this spatial Markovianity justifies building a deformation CTRW in S space, in streamline distance space. We can construct the integrals that allow us to calculate the components of the deformation tensor as shown below. And we end up with a simple random walk. S is the distance along a streamline. SD is the correlation distance, which is fixed. T is the time from one increment to the next in the CTRW, and that varies with the local velocity. And then we can simply increment the elements of the deformation tensor as shown. What this leads to is closed form solutions for this coupled CTRW. So from this CTRW, we can come up with closed form solutions for the elements of the deformation tensor. That's been performed for 2D steady flows and 3D steady flows, and then we can use that to analyze mixing and transport. When we apply this to 2D steady flow, remember for 2D steady flow, we only have longitudinal mixing. There's no three-dimensional element for transverse mixing. what we're interested in is the F12 component of the deformation tensor. It grows due to shear, and it can fluctuate due to local velocity fluctuations. Very often for porous media flows, the velocity distribution has a power law tail, so it can be shown as v to the power of 1 minus beta, where beta is a parameter of the flow. And for various values of beta and also alpha, gives you the correlation between the velocity gradient and the local velocity. We get different algebraic stretching regimes. So this off-diagonal element F12 of the deformation tensor, which essentially is the only way that fluid elements can grow, that's predicted to grow algebraically with time as t to the power of r, and r lies between 0 and 2 for different values of alpha and beta. Now we find different scaling regimes for r based on the types of dynamics that we see. We can see linear stretching with time, superlinear, and almost ballistic growth of fluid elements, and then ranging right down to sublinear growth. So by solving this problem, we essentially have closed form solutions for the stretching of fluid elements in these relatively simple steady 2D flows, and then those stretching rates can then be placed within the lamella mixing models to give us ab initio predictions of the solid concentration PDF. Note there's no transverse dispersion in this system because the ensemble average of the transverse components of the deformation tensor is 1, and it's only F12 that quantifies the longitudinal dispersion. So now for these relatively simple, but still highly heterogeneous steady 2D flows, we can make complete predictions of the evolution of solute mixing and dispersion from first principles, and these match very, very well with fully resolved computational studies. When we consider 3D steady isotropic Darcy flow, the picture is very similar. And this is again because these flows have 0 helicity density. They emit these 2 dual stream functions, psi1 and psi2. And for this system, because this flow is helicity free, the 2 shears within the system essentially decouple. You can show directly from the helicity free condition that epsilon 2,3, the epsilon 2,3 component of the velocity gradient tensor is 0, and the Lyapunov exponent is 0. And these flows essentially behave like 2 2D flows that are superimposed orthogonally with each other. So there's no coupling between those 2 two-dimensional flows. And so then the kinematics of these flows are actually very similar to two-dimensional flows in themselves. Because of this, all the diagonal components of the deformation tensor simply fluctuate, and the ensemble average of those is 1. And then the only components that grow with time are now the F12 and the F13 components. So these are again these shear components. Now one is in the 1,2 direction, and the other one is in the 1,3 direction. And the dynamics is very, very similar to two-dimensional flow. So because of that, these 2 components, F12 and F13, again grow algebraically with time as t to the power of r. And once again, we find r is dependent on these parameters alpha and beta that capture the coupling and the correlation structure of the flow. Again, there's 0 transverse macro dispersion as F22 and F33, the ensemble average is 1. And so these are not very good models of real flow in porous media, because we know from experiments that real porous materials in fact exhibit significant transverse macro dispersion. The other issue that needs to be highlighted is that conventional numerical schemes to predict macro dispersion also don't preserve this constraint. So there's a lot of danger to generate spurious results and then interpret that as representative as reality. So at the end of the day, 3D isotropic Darcy flow has the same kinematics as just 2 superposed 2D flows. And so from the basis of that, we'd say these aren't very good flows of real porous materials or models of real porous materials. This picture changes completely when we consider anisotropic Darcy flow. So for isotropic Darcy flow, the conductivity or the permeability of the system is a scalar. For anisotropic flows, this is now tensorial. We can consider the simplest tensorial model given here. So we have 3 elements on the diagonal, K11, K22, K33. And we can show very simply that this system is non-zero so long as one of the components is different to the others. When we consider these sorts of systems, we can consider the braiding of streamlines as they move through the flow, and that braiding increases with the log variance of the conductivity field. So for small log variances, sigma squared log k is 1. We see oscillation of the streamlines, but very little braiding. As we go up to highly heterogeneous systems, these anisotropic flows then impart strong fluid braiding, as shown on the right, for sigma squared log k is 4. Now, this is very different to what we saw on the previous slide, where even for very heterogeneous flows, no matter how heterogeneous, they were still non-mixing and non-braiding flows because of their non-helical nature. Now these flows have helicity throughout, and that allows the streamlines to braid, and so we can see complex mixing behavior. If we go back and look at the deformation CTRW for this case, we find that it's a mixture of algebraic and exponential, and the exponents R and the Lyapunov exponent lambda infinity are computed on the bottom right for various values of the heterogeneity, sigma squared log k. And we see here that as expected, with increasing heterogeneity, the strength of both the Lyapunov exponent and that algebraic index R both are monotonic increasing. And if we make direct calculations of that and compare with braiding theory, we get a very good fit between the two. So essentially for these sorts of systems, they're definitely chaotic. The mixing dynamics would be expected to be much richer and stronger than that for the isotropic Darcy flow, and Lyapunov exponent and the longitudinal and transverse deformation increases strongly with heterogeneity. Now let's change gears and have a look at some unsteady flows, and we need to update our stochastic framework for unsteady flows, because now we have the opportunity for our flows to decorrelate in space and time. So for unsteady flows, as we just said, the velocity can decorrelate in space and time. If we have 2 steady flow velocity fields, V1 and V2, and we construct an artificial unsteady flow via random forcing between those two, well, then there is 2 means of decorrelation for a fluid particle. So the velocity of a fluid particle can decorrelate by moving in space in flow V1 or V2, or it can also decorrelate in time based on the switching f of t, the function f of t that controls the switching between the 2 flows. So if we consider SD and TD to be the decorrelation length and the decorrelation time for the velocity and this switching function, then we can write an overall correlation that is the product of 2 first-order decorrelation processes. And so essentially what comes from that, because these systems are Markovian, decorrelation of the velocity occurs when the variable r, which we define as s on SD plus t on TD, is greater than or equal to 1. So we've constructed this correlation variable r based on the decorrelation length and the decorrelation time under the assumption that these 2 processes are first order. When that decorrelation variable is 1 or larger, the system is decorrelated. And so the velocity along a path line in these flows is Markovian in R space. It's not Markovian with respect to S, it's not Markovian with respect to time, but it's Markovian with respect to R. And so now we can develop the CTRW for the evolution of velocity in R space. So our CTRW now is R just increases by 1 at each step in the process, S increases by delta Sn, and T increases by delta Tn, where delta Tn and delta Sn are dependent upon the local velocity Vn and the decorrelation length and time. And so from the plots along the bottom, we have for this random process, for this model flow, On the left, we have the velocity as a function of time along a path line, and so you can see that that is quite intermittent. The velocity in the middle, the bottom middle plot, is the velocity as a function of path lengths, streamline distance, and you can see that that's intermittent. But then when we plot the velocity as a function of r for this flow, no matter the magnitude of SD and TD, this is then Markovian, and so that gives us a good basis for a random walk model. We can apply that to our deformation CTRW, and we can look at the R-space velocity PDF. And for this flow, again, we find that the only component for a 2D flow, the components that we need to worry about is the F12, which grows as a shear. And when we solve the deformation equation for that, we find that that is just equal to a constant times F11 of R, and F11 and F22. F11 grows as exponentially as the Lyapunov exponent, and F22 shrinks exponentially as the Lyapunov exponent. So in this case, the growth of F11, F22, and F12 are all dictated by the Lyapunov exponent itself. And we have a very simple understanding of deformation in these flows. We can characterize the Lyapunov exponent, as we've done for the previous cases, as a function of heterogeneity of the system, and as expected, the Lyapunov exponent increases monotonically with heterogeneity. But what is interesting is that the Lyapunov exponent passes through a maximum with respect to the decorrelation time of the switching process, and that makes perfect sense because for short decorrelation times, i.e. very fast switching, the effective flow is just an average between the two. Likewise, in the limit of very slow switching, essentially we've got a steady flow that very, very rarely switches to the other flow. And so the best mixing and the best, the fastest mixing and the fastest rate of growth of material elements is given somewhere between those two limits. So we find for this system that we can again characterize the deformation tensor, and the step down the track here is now to build models for solute mixing and so on based on these deformation rates. I won't get too bogged down into this example here, but here we're looking at 3D unsteady pore scale flow, and this is essentially a model of the deformation of fluid elements in that push-pull flow. The push-pull flow can also be modeled as a time periodic sine flow, and what we do to analyze and understand transport in this flow is we make the time periodic sine flow reversible. So we run the flow forward in time and then backwards, and we look at advection and diffusion under this scenario. Because of reversibility of this flow and the periodicity of the system, the Eulerian and Lagrangian frames coincide at periods of the flow. And so the concentration field is driven by the highly anisotropic effective dispersion tensor of this system in the Lagrangian frame. So we've computed the eigenvalues of that dispersion tensor shown on the bottom right here. And we see that we get these regions, these highly anisotropic regions of very high diffusion. And in fact, when we do numerical experiments of advection diffusion in this system for this model push-pull flow, we find indeed that those manifolds of very high dispersion map exactly onto evolution of the solute plume. And just to remind you, this was the push-pull flow for the experimental system, and we compare that then to our model sine flow as shown. And this was the key really to being able to understand and quantify mixing from those experiments. So how do we pull out the mixing dynamics and the Lyapunov exponent? So this type of model essentially allowed us to understand how deformation controls mixing in this experiment and make a connection between the Lyapunov exponent and the measured concentration field. Okay, one other matter that I haven't touched upon is we've really assumed through all of this that the mixing dynamics are homogeneous throughout the porous medium, but of course, as we saw in earlier on, many unsteady porous media flows exhibit heterogeneous Lagrangian topology. So we have these isolated mixing regions, we have these chaotic seas, we have regular regions and so on. And essentially what we need to do is develop tools to characterize the mixing dynamics in each of those individually when this heterogeneous Lagrangian topology arises. An outstanding challenge is to develop global transport theories on the basis of that, but that's a next step down the track. Okay, so to summarize, how do we apply all this to data sets? If we have computational or experimental data sets of solute mixing at the pore scale or larger scales, how can I predict that? And essentially, the recipe as follows shows how to do this. For 2D or 3D steady and unsteady flows, we must characterize the PDFs of velocity, velocity gradient, and look at the correlation structure of velocity. We then need to solve the deformation tensor using a CTRW, and that essentially gives us stretching rates for the elements of the deformation tensor. Those stretching rates then go into dispersion and mixing models for the local concentration PDF. And so far, these have been developed for steady 2D and 3D flows, and we need to develop those further for 3D unsteady flows. And then finally, you can implement those mixing and dispersion models as subgrid models for a solute plume. So say, for example, we have a coarse computational grid. We might want to capture the dispersion and spreading of the solute plume on that grid, but carried with that grid is a subgrid model for fluctuations in concentration below the grid resolution. Okay, so to conclude, our findings are that if we have porous media flows that span from simple to complex Lagrangian kinematics, we have rich data sets now to observe these, and we've developed a stochastic framework that resolves these kinematics. The key point is that fluid deformation governs mixing and transport. A protein frame is convenient and properly resolves the constraints of Lagrangian kinematics, and deformation across diverse flows is characterized by the velocity and velocity gradient statistics. This deformation CTRW gives us an ab initio stochastic framework and allows us to predict deformation, and then those deformation rates provide inputs for models of solute mixing and transport at the pore or Darcy scales. So the future challenges here is we need high resolution data sets that resolve both the velocity and the velocity gradients, and we need robust construction methods for those data sets. We need to develop further mixing models for 3D unsteady flows and extend the framework to 2D flows. And further work is required to link medium properties to deformation rates. With that, I'll say thank you and acknowledge our sponsors, and also advertise that we're looking for a PhD, joint PhD between RMIT Australia and the University of Rennes. Thank you.
Thanks, Daniel. It was an excellent talk. I'll open the floor up for questions, but I'll take the liberty to proceed with the first question. Daniel, I was just wondering about the push-pull experiment. Can you just explain how that actually takes place? Because do you actually have suction and ejection as well through that spot?
Yeah. I believe. I mean, these experiments were undertaken at the University of Rennes in France, and they used a syringe pump in which they would. So you'd first of all set up a steady flow through the porous medium, and inject a thin needle, inject a dye at the same velocity as the background flow. So you'd set up. You could imagine you've got this three-dimensional column vertically, and you'd set up pretty much a steady plume through that experiment. Once that steady plume was established, then you would stop the flow and stop the injection of dye, and then withdraw the fluid. And so that's what you're seeing in this video here, is as you're withdrawing the plume back through the injection plane, shown here in blue, that's the dye trace that comes through.
Oh, right, okay.
Okay, so in the absence of diffusion, that would all collapse back to the ellipsoidal cross-section. And so the only reason you're getting that is because of diffusion and the deformation history.
Oh, right, okay. Because I was wondering, when you actually suck it back, wouldn't that dye, go back into the pipe from where it has been.
Look, in the absence of diffusion, absolutely. If we could all collapse back, I mean, assuming that your experiment is set up properly, the flow should be fully reversible and it should collapse back. But because we see that exponential enhancement of diffusion and dispersion because of the stretching, all that stretching is undone. But remember that mixing is a function of stretching history. So that's the signature that we're seeing there. And then the tricky part then is then making the connection between what you're measuring and what's actually going on.
All right. Of course, the time scales at which that ejection and suction process happens is much smaller than the diffusion time scale.
Yes, but also because you're getting exponential enhancement, even if that time scale is small, the signature is still significant.
Okay. Yeah. Do you have any questions from the audience? Please feel free to type it in the chat and I'll read it out if you don't want to unmute. It's fine.
I've got a quick question.
Yeah,
so this was on the 3D steady isotropic Darcy flow. I think you have a slide on that. So I thought it was a really cool result that you had, that you're saying it was more like 2D kind of flows overlapping on each other.
Yeah. No, it's it took us a long time to convince the community that this was real. These models have been used for a very long time, and as I said, the real red herring here is that the numerical techniques that people were using to study these flows don't follow these streamlines. If you have a bog standard naive particle tracking routine and it doesn't know about this structure to the flow, these numerical errors that are always going to be there make it look like the streamlines are braiding with each other and make it look like the streamlines can spread without bound. I mean, you can understand the concept that if you have a two-dimensional flow, the streamlines can't spread without bound if they're steady, because there's nowhere for them to go. There's a topological constraint there. Now, these flows kind of have, even though they're 3D, they have exactly the same character because everything is constrained to these pairs of stream surfaces.
Wow. Yeah, I thought, I just was really taken aback by that result. I thought it was really cool. And I guess, my question was going to be, I think it's probably a bit unfair, but do you have any ideas about then how the numerical schemes could even be updated for something like this?
It's actually relatively straightforward. What you can do is essentially base a stream, do your particle advection. First of all, you'd have to compute the stream functions and then do your particle advection with respect to those stream functions.
Okay.
So essentially so you can imagine you have two stream functions where they intercept forms a streamline, and along that streamline, that's where your particle tracking has to happen. So the only thing you actually need to compute is the distance along that streamline. So if you set your routine up that way, you're only doing an integral essentially to find out how far have I moved along that, and then all those constraints are there. That's a fairly simple thing to fix. The problem, however, though, is that all of the dynamics and the kinematics of these flows suddenly start looking nothing like reality. And as I said, that to me, it's more like these are bad models of real natural systems because they constrain the physics too much.
Oh, thank you. Thanks for answering my question.
No problem.
Guy Metcalf just put it in the chat. Thanks, Dan. Nice talk. Daniel, just another quick question. I was just wondering with your when you showed the first slide, so what that means is if you can actually map the geometry of that porous media, you can very, very closely say where or how the fluid will behave, because it would obviously go through the gaps that the structure has, which in this case, if you look at it, it looks like those pores are, I think, hexagonal in shape.
Well, these are, you can kind of see it in the image here. These are randomly packed glass spheres. And so you can see the PIV particles sitting around the spheres. In this case, we would consider this to be a granular media. Okay, it's very simple,
Okay.
but it's still a granular medium. What gives all of the fluid stretching and folding is the contact points between spheres. So you can imagine whenever your plume hits a contact point between spheres, part of that plume is held up at the contact point and the rest flows downstream. So that sets up very strong stretching of fluid elements locally. And that's the mechanism that drives stretching and folding. So if we're going to understand evolution of this plume, the thing to do would be to, if you could image the spheres and say, okay, where are all the contact points? Finding all those contact points would tell you a lot about how that diplume has evolved in the way that it's evolved.
Well, yeah, makes sense, yes.
Daniel, very interesting talk.
Thank you.
Well, I was just wondering that with this framework, typically in engineering, one would require, for example, large-scale dispersion coefficients, not the molecular one, but the turbulent or the mixing one. So how do you go from? Is there a way you can use this framework to predict the large-scale dispersion coefficients?
Yeah, so that's absolutely one of the goals. But perhaps something that I skimmed over is in this example. Where are we? Here. Okay, so I've denoted D noughts in the black boldface to be our local dispersion tensor. I mean, that could be a molecular diffusivity, or it could be a local dispersivity. The whole idea with this framework is to say, okay, what mixing characteristics do you get, and also what macro dispersion characteristics do you get? So that's one of the goals here. We're not necessarily constrained to having molecular diffusivity as an input or local dispersivity, but certainly what we'd like to come out is ideas of macro dispersion and so on.
Yeah, so given molecular diffusivity, which you know, do you predict from here the macro dispersion coefficients?
Yeah, so I guess, so the deformation tensor here tells you things about the spreading of material elements, and that's purely kinematic. Okay, so there's no interaction between diffusion and kinematics here. But colleagues of mine, especially colleagues in France, that's their bread and butter, is to take that information, and I didn't really touch on that too much today, and then calculate an effective dispersion coefficient from that. The problem is, though, is these systems are generally non-Fickian in that it takes a very long time for them to reach the Fickian limit. And so people don't talk about macro dispersion coefficients so much, but they use, again, CTRW frameworks and so on to characterize these processes.
Right.
But yes, in principle, all the ingredients are here to use that. I sort of focused more on mixing in this talk, though.
Right. Thanks, Dan.
All right. If there are no more questions, please join me in thanking Daniel for an excellent talk. And we'll see you next week. Thanks, everyone.